to go. I just wanted to make sure that I show you how to calculate a photolysis rate constant, because if you choose to do photochemistry in your Kinetica project, you're going to have to make some assumptions about calculating the rate constant. Okay, so let's do that. So I'm going to show you my model. So I've still got this hydrogen-bromine reaction, right? But now I added in a photochemistry model. Okay, and so here it is. So the mechanism is very similar. However, in that very first step here, there's my first step. There's no bromine plus M, right, to make the collision happen. It's just bromine absorbs a photon, and that photon directly leads to the production of bromine radicals. I think that I've got that. Yes, here we go, right? So in these linear chain reactions, this is kind of the last and final subject, right? We can initiate a chain reaction through heat, right? Oops, undo. So we can initiate it with heat, or we can initiate it with light. Both cases produce bromine radicals. Okay, pretty cool. And so now that's an initiation step. There, I've showed it to you, K1, okay? So in these linear chain reactions, anything that continues making more radicals, we call propagation. So you can see in the next step, whether it's initiated by heat or light, a bromine radical does a hydrogen atom abstraction on H2, right? So something like this. Okay, so it undergoes the fish hook mechanism, okay? And that makes a stable HBr, but it propagates the radical cycle because it's kicking out another hydrogen radical. Now, if there's an equilibrium of that, or in other words, if it takes that newly formed radical and pushes it back to stable product, we call that inhibition. Because ultimately that's going to limit the rate of this reaction, right? HBr is the final product we want to make. However, in this reaction, HBr is getting consumed backwards, right, to more reactants. So we call that inhibition because it's inhibiting this radical cycle. Okay, then we get another step, okay? So then now this H radical, so we produced another H radical that can then produce another bromine radical. So that's more propagation. And now finally, so this is why these two initiation steps aren't shown as an equilibrium, because now these two bromine radicals reforming via a third body reaction doesn't produce any more radicals. So it's a termination step, okay? And that's the only way these types of chain reactions stop, is not necessarily when you run out of reactant, rather when you run out of radicals. So we might have unreacted bromine or unreacted H2 depending on the conditions of this chain reaction. Okay, so now this is a 45-minute lecture. Oh my gosh, I'm sorry. I just want to talk a little bit about this now mechanism with light. And so I'll just compare this. So these were the results I did when the reaction was driven by heat. And I'll remind you of my conditions. 1200 Kelvin. I've got a third body in there at 1 atmosphere, okay? An inert third body. And my initial bromine and hydrogen are very low at 1017, so that's roughly 100 times less than the concentration of my bath gas, okay? So roughly like 0.01 atmospheres of bromine and 0.01 atmospheres of hydrogen and 1 atmosphere of inert third body. And at 1200 Kelvin, this reaction is crazy fast, right? It's over within 1 millisecond, okay? You can see bromine and hydrogen decay, and bromine is decaying at a different rate than hydrogen, and that's actually due to that 1/2 order interesting phenomenon of bromine. And I would definitely say bromine and hydrogen, even though it looks like they're produced at steady state, they are not, because this is a log scale. right? You can see there's a huge production of bromine radicals, right? It spikes up like 5 orders of magnitude, okay? And then later on in the reaction, it starts to hit a steady state. So let's compare that now to the reaction driven by light. And the only thing I changed in this mechanism is I dropped the Br2 plus M and just make it Br2 plus H nu. And then here my K1, right, is just phi times sigma times F. I assume my phi to be 1. There's my sigma, right, my cross section. And I said flux is power divided by energy, where energy is Hc over lambda. Okay, so I solve all those problems. Here, I'm making the temperature equal to 350 Kelvin, and I'm using a 100-watt lamp at 1 square centimeter. And these are the results. Completely different than the reaction initiated by heat. For one, look, it takes 100,000 seconds for this reaction to proceed versus the 1 millisecond, right? So 100,000 seconds is several hours, all right? The other thing you notice is bromine and hydrogen are absolutely produced at steady state throughout the entire reaction. Look at this. Almost instantaneously, bromine radicals are generated at a really large concentration, which is really cool. So that photolysis step is really fast. It's generating bromine radicals immediately, but what it's doing is it's generating bromine radicals at a steady state. You also notice that it's producing hydrogen at a fairly steady state. However, the concentration of hydrogen is way smaller than the concentration of hydrogen generated up here, right? Hydrogen spikes about 10, 13 molecules per cubic centimeter, and the reaction driven by light, hydrogen barely hits 10 to the 7 molecules per cubic centimeter. So huge differences. And I'm also going to change this log scale just so you can see it in a little bit more detail here. Let's hope that works. Yes. So you can also see you can't even distinguish bromine and hydrogen because I set them both to be the same concentration. If let's say I make bromine like just a little bit different, you'll be able to see now super dynamic, right? They're not necessarily the same. You can see HBr is produced really quickly right away, but then tapers off and starts undergoing a steady state production. Okay, so these reaction profiles are just completely different, whether driven by heat or light. And we could really dive into like all these steps, what's going on there. But that's what I want you to do in your project. I want you to think about all these steps that are going on, kind of like how I described them, by noting, look, steady state production of bromine. So there's always a steady production of bromine radicals. How is that going to influence the reaction down the line? Okay, so this stuff gets really, really interesting. I could also play with this and I could turn down the power of my lamp and see how that changes the reaction. I could, I had to make this go at about 350 Kelvin to see something reasonable. I could certainly turn this down to room temperature and see how that plays out, okay? So all interesting stuff that I want you to kind of self-discover in your Kinetica project, all right? Sorry that I went a little long on this one. I will see you on Friday.